All right. All right. So I'd like to welcome everyone to Sabina Nketia's PhD defense. My name is Tom Shi. I am Sabina's PhD advisor. Sabina got her Bachelor's of Science in Aerospace Engineering from Carleton University in Ottawa, Canada in 2016. Her degree was in Aerospace Engineering. Sabina has a Master of Science in Aeronautics and Astronautics from Purdue in 2018. After her Master's, she started working with me on her PhD, and today is her PhD defense. Now, for her PhD defense, she'll give a talk for about 45 minutes. During that part of the talk, if you have questions on clarification, please do ask, but if you have other questions, please hold off until she finishes her talk. So after her talk, we have the Q&A initially opens up to the entire audience, and so anybody can ask questions. Then once the audience finish asking questions, then I will stop the Zoom, not to stop the Zoom, but stop the recording. At that time, the committee will start asking questions in a closed meeting. So with that, then, Sabina, the floor is yours. So please share your PPT.
Thank you very much, Professor Shi. I will share my screen in a minute. Okay. Sorry, I'm trying to share. I don't okay, yeah, sure enough.
Go ahead, sure.
Yeah, good morning, everyone. My name is Sabina Nketia, and for my PhD final examination, I'm going to be talking about large-eddy simulation of rotationally and externally induced ingress in an axial seal of a rotor-stator configuration. So for today, I'm going to start with a brief introduction, and then we'll go over some literature review. Then we'll talk about the objective. Then we'll describe the problem that we are trying to solve. After that, we'll talk about problem formulation, numerical method of solution, and then we'll do some cases for verification and validation. After that, I'll present results, and then I'll summarize and conclude on the talk. So in gas turbine engines, the hot gas going from the combustor into the turbine section can be as high as 2000 degrees Celsius. Some of this hot gas goes into the space between the stator disk and the rotor disk, which is known as the fill space. Now, this ingestion of hot gas into the hull space can cause a catastrophic failure of the engine. So this needs to be prevented. To prevent this, we pump a cooler flow known as sealing flow or purge flow from the compressor upstream onto the bottom of the hull space to counter this. Now, this sealing flow must also be minimized because it can be used to generate power to increase the efficiency of the gas turbine engine. And to be able to do this, reduce sealing flow and then also reduce hot gas ingestion, we need to be able to design better rim seals. That is the place where ingress occurs, the connection between the stator disk and then the rotor disk. Now, to be able to design better rim seals, we need to understand the fluid mechanics and then the geometry and fluid mechanisms of everything, flow mechanisms and how things go into the seal. Ingress is induced by the rotor disk and its rotation, which is known as rotationally induced ingress, and the pressure variation about the stator vane streaming edge, which is part of externally induced ingress, and then the oscillations in the stagnation pressure created by the rotating blades. Today, I'll be talking about rotationally induced ingress and then the pressure variation about the stator vane streaming edge, which is a part of externally induced ingress. So for both rotationally induced ingress and externally induced ingress, a lot of experimental and computational work has been done, which I show in the pie chart. From the literature review, several non-dimensional parameters were seen, but the most interesting ones are the non-dimensional sealing flow rate, which is CW, and then the Reynolds number in the annulus, which depends on the annulus hydraulic diameter, and then the external Reynolds number, which is also a Reynolds number in the annulus, but it depends on the radius of the hub, R0, and then also the rotational Reynolds number, and the ratio of the external Reynolds number to the rotational Reynolds number. And all these parameters are varied to see how they affect the coefficient of pressure on the stator platform, known as CP, which has been said to be a predictor of ingress, and then the sealing effectiveness, which is how well the seal is able to prevent hot gas ingestion. So there are some parameters that I think are key here, but I'll talk about them later on. So the following was noted from the literature. From the literature, when REW, or the ratio of the external Reynolds number to the ratio of the rotational Reynolds number, is much less than 1, then it means that it is rotationally dominated, means that the ingress is dominated by the rotation. But when it's greater than or equal to 1, then it means that it is dominated by external influence, that's the stator vanes and other things that are not part of rotation. So far, benchmark quality data has been generated that can be used to validate CFD. That is from Green and al. In Ohio State University or from Sangan and al. At Bath. But they focused on generating high quality data and not so much on talking about the physics. On IR ingress, Kelvin-Helmholtz instabilities has been identified by Raps and al. In their 2009 study. However, how they occur and how they affect rotationally induced ingress was not explained. Also, alternating regions of high and low pressure regions have been identified by Green and al., but what causes these regions has never been identified. Then there's been some conflicting statements about the trajectories of flow in the seal. And then RANS cannot predict RI ingress, that's rotationally induced ingress. And then so far, LES studies have been done, but they were done on coarse mesh and they did not address certain key criteria like the tele criteria. And then also there wasn't great sensitivity study done. On EI ingress, from the literature in Sangan and al., CP or the coefficient of pressure was deemed as the predictor of egress, but we would want to verify this. Also, pressure induced by the vane dominates, the pressure induced by the vane was seen to dominate ingress from Roy and all in their study, but we want to understand how only rotation can affect the ingress and egress. And then again, RANS cannot predict externally induced ingress from Liu and all in their study from Purdue. And then LES studies done so far was done on a coarse mesh from the study by O'Mahony and all. So this is just a summary of what the key stuff that I found from the literature. So hence my objective is to examine the flow mechanism creating rotationally induced ingress in a Rotor-Stator configuration using well-resolved LES. The approach would be to use a Rotor-Stator configuration without vanes and without blades. And then the second objective is to assess the accuracy of LES and RANS to predict flow mechanisms creating externally induced ingress by stator vanes. Here, the approach would be to use a Rotor-Stator configuration with vanes and without blades. So for my problem description, I'm going to, sorry, let me just move the chat somewhere. Okay. So for my problem description, this is the configuration from the Aachen group, and this is the configuration studied for rotationally induced ingress. It has no vanes, and then it has no blades. So here we have the hot gas coming in at a hot temperature and then velocity profile, and then it goes, and then this is the seal here where it's between the stator disc and then the rotor disc. And then we have the outlet where there's a back pressure. And then we have an extension duct to prevent reverse flow. And then at the bottom, we have the cooler flow coming into the seal at a cooler temperature. And then the red boundary is a rotor disc rotating at an RPM of 11,700 RPM, which is representative of aircraft aircraft engines, really. And so some of the key dimensions that I would like to note will be SC, which is the gap width, and then also R0, which is the radius of the hub of the rotor disc, and then also VH, which is the velocity coming into the annulus of the hot gas, and I think S, and then DC. These are some of the key dimensions that I'm going to talk about. On the left-hand side, we do have the dimensions summarized. Now, this configuration and operating conditions were taken from Bond and al. In their 1995 study. So for this configuration, I ran 2 cases for it. So again, no vanes, no blades. It's an axial seal. I'm using the LES wheel model, a 10-degree sector. And then here I'm using a fully developed velocity profile from LES with the fluctuations from synthetic turbulence. And then the first one is one that has data from experimental data for validation. Then the second one just has a ceiling flow of 0, which is to just study the worst case scenario to see what happened. And again, the rotor angular velocity is 11,700 RPM, representative of aircraft engines. Now, these are some of the interesting non-dimensional parameters that were obtained. So for the first case, 1,000, the non-dimensional ceiling flow rate is 1,000, and then the second one is 0. So that's why I made 1,000 over 0, but they are not divided, it's just 1,000 or 0. And then I have the annulus Reynolds number, and then the external flow Reynolds number, and then the rotational Reynolds number, and then the ratio of the external flow Reynolds number to the rotational flow Reynolds number, which I highlighted, is 0.41, just much less than 1. So rotation is very dominant here. The second configuration, the second problem that I'm going to solve, which meets the second objective, is from the bath configuration, which has 2 veins. Actually, it's 32 veins, but I'm using 2 veins here, and 2 vein passages here. And again, we have the hot gas flow coming at a temperature, and then the cold gas flow. And then we have our rotor disc, extension duct with the back pressure. And then also the green here are my stator veins. And then I have my SC. But note here that here the rotor disc is a step below the stator disc. And so I put an inset here, and it's also inclined at an angle. So it's not the usual 90-degree inclination that we know. It's just at an angle, and it's a bit of a step below the stator disc. And I'll talk about the importance of this later on. So here for this configuration, actually I ran 2 configurations for this. For the first configuration, it's the same, but I took out the veins to see how, if you take out the veins, what happens to the sealing effectiveness and to the flow. And then also here, one thing I did was that I made the hot gas temperature the same as the cold gas temperature. And to offset for the differences in density, I added 5% carbon dioxide by mass to the sealing flow rate to make up for the density change. And note here that the rotor angular velocity is 3,000 RPM, which is representative of land-based gas turbines. And again, I show the non-dimensional parameters that are interesting in this flow. So CW, REDH, REW, RE5, and then here REW over RE5 is 0.538. This was what the experimentalists prescribed as the desired operating point for this configuration. So now I talk about my formulation. For my LES formulation, I'm using the specially filtered and steady 3D continuity, species and momentum, full compressible Navier-Stokes and energy equations with temperature-dependent properties, thermally perfect gas, where the turbulent Prandtl number is 0.85 and turbulent Schmidt number is 0.7. I neglected the Soray and Dufour effects, and then also I'm using the LES wall-adapted local eddy viscosity turbulence model. For rotationally induced Ingress, that's the Aken configuration. The fully developed the velocity profile was obtained from LES, where I ran a very long duct as a translationally periodic duct, and I found the mean velocity profile, and then I ran another duct to see how long that duct needed to be to get that same fully developed flow if I use the mean plus the synthetic turbulence specified. And I have the sealing flow rate, the pressure at the annulus outlet, and then the rotor disc angular velocity. Now, for the externally induced ingress case, again, fully developed flow from LES. However, there, they gave us a really long duct, so we were able to run it to get the fully developed flow that we needed. And then again, I have my sealing flow, mass flow rate at the sealing flow with 5% carbon dioxide by mass to offset the density difference between the hot gas path and then the cold gas path. And again, I have my back pressure and then a rotor disc angular velocity of 3,000 RPM. Here, for RANS, okay, so even though the study is mainly about LES, I used RANS as my initial condition to start the LES. So I ran some RANS, and then also I do some comparison with RANS, that's the Reynolds average Navier-Stokes equation. And so I ran that too. And the formulation for that, I use the Reynolds average 3D continuity, species and momentum, and the energy equations with temperature-dependent properties, thermally perfect gas, a turbulent Prandtl number of 0.85 and a turbulent Schmidt number of 0.7. Again, I neglected the Soray and Dufour effect, and I'm using the shear stress transport model. And for the RANS simulations that I did, I used a mass flow inlet for the annulus, not a velocity profile, and also all the boundary conditions specified are mean quantities. For my solution method, the code I'm using is, or I used, was ANSYS Fluent version 22.1. Then the algorithm for rotationally induced ingress, that is when there are no veins and no blades, I used a simple scheme. And for my time derivative, I used a bounded second order implicit scheme. And then for spatial derivatives, I used the Presto for pressure interpolation, second order central for all advection and diffusion terms. For externally induced ingress, when there are veins, I used the couple scheme, the bounded second order implicit scheme, and then the second order central for all advection and diffusion terms. For my time set size and grade, I'm going to give more details in the verification and validation section. However, I use 10 raised to the power minus 6 and 10 raised to the power minus 5 for my time set sensitivity. And then I make sure that for all my grades, the y plus next to the wall of the first grade points next to the wall was less than 1, and there were at least 5 grade points within the y plus of 5. At the end of each time step, the residuals for continuity was less than 10 raised to the power minus 6. For momentum, it was less than 10 raised to the power minus 7. For energy, it was less than 10 raised to the power minus 8. And when there was carbon dioxide, or if there's carbon dioxide, it was less than 10 raised to the power minus 8 for the CO2 concentration. Typically, for these configurations that I've shown, about 40 to 60 iterations per time step were needed for convergence. Now, for my runs, again, I use the ANSYS Fluent version 22.1. I use the couple scheme, and then I use the second order central for all advection and diffusion terms. And again, my grade size met these criteria. Then for convergence, residuals was, the residual for continuity was less than 10 raised to the power minus 6. And then for momentum, 10 raised to the power minus 7. And then for energy, 10 raised to the power minus 8. And CO2 concentration, 10 raised to the power minus 8 as well. So I move over now to the verification and validation section. And so where I make sure that I'm solving the correct equations, and then also I'm going to make sure that I match with experimental data, that is validation. So I'm going to talk about 3 cases. The first case is going to be an annular duct because all my rim seal configurations are starts with an annulus or an annular section. Then the second one is going to be an annular duct with a rim seal with no vanes and no blades, which is representative of the Aachen configuration, the configuration from Aachen for rotationally induced ingress. And then the second or the third case that I'm going to run is a rim seal with stator vanes but no rotor blades, which is representative of the bath configuration. So here I'm running an incompressible fully developed flow in an annulus, and I have experimental data from Nuru and al. In their 1993 study. And so I'm going to run this as an incompressible duct, as a translationally periodic duct, which is going to be like infinitely long, but it has, I gave it a length of L5, which matches some requirements that were given. And I ran it as translationally periodic such that what goes in comes out and what comes out comes back in. So it looks like an infinitely long duct. And I was given the Reynolds number where I was able to calculate the bulk velocity and then also the temperature that was required for it. Now for this formulation, I'm running it as an incompressible duct, specially filtered and study 3D continuity, species and momentum, Navier-Stokes and energy equations with LEA's wheel turbulence model. And here, the velocity is based on incompressible fluid developed flow. I generated initial turbulent fluctuations by this command in ANSYS Fluent. I used a simple scheme. And then for the time derivative, I used the bounded second order implicit scheme and also Presto scheme for pressure interpolation and second order central for all advection and diffusion terms. At the end of each time step, residuals for continuity was less than 10 raised to the power minus 4, for momentum was less than 10 raised to the power minus 5, and for energy less than 10 raised to the power minus 7. Typically, for this particular simulation, about 10 iterations per time step were needed for convergence. So when I'm using a sector size, not the full annulus, and so the sector size needed for LES should be big enough to contain the flow structures in the flow. Now, this sector size needed, or which will be sufficient, depends on the curvature parameter gamma. And if gamma is much less than 1, then the effects of curvature can be neglected and the flow can be treated as planar flow. So in this particular flow, gamma is about 0.5. So for planar flows, Kim and all in their 1987 study recommended a span-wise dimension of 3.2 times the gap height, which is equal to about 90 degrees for this problem. However, a 2-point correlation in the span-wise direction for this same problem by Quadrio and Lucchini goes to 0 at about a quarter of that span-wise direction. But decided to use 120 degrees to see how well this fits in, how well it will perform as compared to what was shown in literature. The time step size for this problem prescribed by the DNS study was 4.1 times 10 to the power minus 6. However, I did a time step sensitivity study with 2 time step sizes, 10 to the power minus 5 seconds and 10 to the power minus 6 seconds, to see which one works well. And I will show the results later. For this problem, I had 3 grades: a course grade, a baseline grade, and an defined grade. And all these grades met certain criteria of the Y plus of the first grade point of the wall being less than 1, and then these maximum delta R pluses, R delta theta pluses, and delta Z pluses. So I'm going to talk about the Chelle criteria here. The Chelle criterion shows that the LES IQ for each grade that is used must be greater than 0.8, which means that we need to, every grade that you use for LES must be able to resolve more than 80% of the turbulent kinetic energy. From the plot on the right-hand side, all the grades, even the course grade, was able to meet the Chelle criterion. So we satisfied that criterion. And so I show the grid sensitivity study for the time step size of 10 to the power minus 6 seconds, because I did a time sensitivity study, which I won't show here, but I show in my thesis that the 10 to the power minus 6 seconds perform way better than the 10 to the power minus 5 seconds. Yeah. So here I show LES course, LES base, and then define. And from here, the course grade doesn't perform so much from these plots, but the baseline and define grade are in very close ties. So we decided that the grid density for the baseline grade was sufficient for this study. Then also the baseline grade was tested to see if it was sufficient. To test it, we need to look at the energy criteria. And here on the left-hand side, the bottom left, this is the energy spectra of the axial velocity at 3 points: the inner wall, the middle of the duct, and then the outer wall, close to the outer wall. And here you can see that the energy spectra follows the Kolmogorov minus 5/3 law before falling several orders of magnitude. So the grid is sufficient. And then again, I plotted the 2-point longitudinal correlation to see if the duct length that I used, L5, was sufficient. And here becomes uncorrelated real fast, much earlier, which shows that the length of the duct used is sufficient. So I'm going to move to my next case for the verification and validation, which is my annular duct with the rim seal. I'm going to talk about the sector size, the grid sensitivity study, and then I'll do a time step size analysis, and I'll give some validation. So I remind you again of the problem description with no vanes and no blades from the Aachen group. I already talked about the formulation and solution method for this earlier. So I'm going to talk about the sector size analysis with RANS, that's Reynolds average Navier-Stokes equation. So I ran this case for 3 different sector sizes, 10 degrees, 20 degrees, and 30 degrees, to see what changes as you increase the sector size. And I showed the pressure distribution on the hot gas part at R is equal to R naught, that's at the hub. And the variations in the azimuthal direction can be seen, and you can see that, let's say when you have 10 here, when you use a 20-degree sector, you get double of that. And then when you use a 30-degree sector, you get 3 times what you get in the 10 sector, which means that the wavelength of those variations are smaller than the arc length intercepted by the 10-degree sector. So based on RANS alone, 10 degrees is sufficient for this particular case, based on RANS. But then I also have to use LES to confirm or verify what RANS told me. So with LES, I estimated the azimuthal 2-point correlation of 2 points, one of them very close to the rotor disk, which is rotating at 11,700 RPM, and another one a little bit above. And I plotted a 2-point azimuthal 2-point correlation to see if they get uncorrelated. That means the sector size is big enough. And even for point A, which is very close to the rotor disk, you see that it becomes uncorrelated real quick. So the sector size, again, is good enough for this case. Now, this is just for the mass flow rates and then the RPMs specified. If we use different things, we'll have to calculate a different sector that will be needed. So if things change, if parameters change, you have to do a different set of calculation to get a sufficient sector size that you will need. I'm going to talk about a grid sensitivity study. For my grid sensitivity study, I have a course grade, a baseline grade, and then a fine grade. The course grade is really clustered at the walls, but they spread out real quickly, getting to the center of the seal. And the baseline grade has more grid points, but they are evenly spread out. And then the very fine grade has more grid points in the azimuthal direction in the seal region. Again, I'm going to see what time step size that I need to resolve the flow. Now, the time step size needed needs to be small enough to resolve the small scales in the flow, and the Kolmogorov scale can be used to tau eta can be used to estimate the lower level of like the lower boundary of the time step size you need. So from here, you can see that in the annulus, about 10 to the power minus 5 will be good enough. However, in the seal region, which is place of interest, this is where ingress and egress occurs, you need about 10 raised to the power minus 6 to resolve the scale. So 10 raised to the power minus 6 will be used in the results that will be presented later. Now I'm doing a validation. I'm showing that circumferentially averaged mean azimuthal velocities in the seal at 3 different radii in the seal. So here I have my LES baseline, LES course, and LES fine, and then the RANS baseline compared with experimental data. Now, RANS is the solid line, experimental data is the one with the rectangles, and then the LES is in the middle. Now, you can see that for the azimuthal velocities in the seal, LES performs better than RANS. LES gives much lower azimuthal velocities. This is because LES predicts higher turbulent mixing in the seal than RANS. So it shows that, and then but RANS shows higher azimuthal velocity. Now, the LES profiles obtained in this study are similar to those obtained in an LES study reported by Gao and al. In their 2018 study. But we come to the radial velocity in the seal, and here again, RANS is the solid, and then LES is the other one, the dashed line, and then the experimental data is the one with the rectangle. Here it seems that RANS performs better than LES because LES shows much higher magnitudes than RANS for the radial velocity. And then also on the far right, which is very close to the seal where ingress and egress occurs, LES shows an inward radial velocity that which shows that, I mean, very close to the rotor disk, which shows that ingress or rotationally induced ingress occurs on the rotor side of the seal. Now, Born and al. In their 1995 study experimentally observed ingress on the rotor side too, although not measured for the case without rotor blades and without stator blades. Now, again, the LES profiles obtained in this study are similar to those obtained in the study reported by Gao and al. In their 2018 study. I'm going to talk about why it seems that for RANS, for the radial velocity, RANS seems to do better than LES, and see what we were or were not doing right as compared to the experimental data. So for the experimental data or the experimental setup, we assumed that a fully developed turbulent flow was used. So all the cases that we ran previously, or what I had shown, results I showed for, assumed a fully developed turbulent profile. However, because the results from the radial velocity wasn't matching, we decided to try different inlet configuration to see what happens when things change. So we checked another inlet configuration where it's a fully developed mean profile, but with a turbulence intensity of 0%, and then another one with LES, which is uniform flow at the inlet, and then a turbulent intensity of 0%. Now, this is because if the flow is a fully developed profile, but without turbulence intensity, after a while, it approaches a laminar profile, and the boundary layer becomes thicker. And LES is very sensitive to inlet profile and boundary layer thickness and all of that. So from the bottom left, the plot shows that when there's no turbulence intensity, or when the turbulence intensity is 0, this data matches very well with the experimental data, whether it's azimuthal velocity or the radial velocity. However, if it's a uniform flow and the turbulence intensity is 0%, with time, it approaches the fully developed turbulent flow with a turbulence intensity specified. So this means that the flow given in the experiment or the experimental data was not a fully developed turbulent flow with as much turbulence as we had assumed. Hence, the reason why our data wasn't matching the experimental data for the radial velocity. Because here, for azimuthal and radial, if it's fully developed without turbulence intensity, it matches pretty well. Again, I ran another case with no turbulence intensity to see how it compares to when there was inlet turbulence, which is our case that we are interested in. You can see that with turbulence, there are many small structures formed, which is showed from the spectral analysis or the frequency plot. And then without turbulence, only a few large structures are formed. Again, I'm going to show another plot here, which is like a pictorial thing, which shows the top three are three r-theta planes in the seal, one close to the stator side, another close to the rotor side, and then one in the middle, which shows the top one is when there's turbulence, it's a fully developed turbulent inlet with a turbulent intensity. And the bottom one is when it's a fully developed profile with zero turbulent intensity. They are very large structures from the bottom one, but there are a few of them. But for the top one, there are many small structures formed. Again, I show the energy spectra here for different points in the seal region to show that the grid used, the baseline grid used is sufficient. And then these are the spectral analysis of the pressure signal, which shows that there are different peaks that are not defined by a single peak and therefore are not connected to a geometrically triggered acoustic mode. And these peaks are associated to Kelvin-Helmholtz instabilities and vortex shedding in the seal region, because for sensor 4, which is at the bottom, and then sensor 5, which is further down in the wheel space, where there are no Kelvin-Helmholtz instabilities and vortex shedding, there's not a lot of energy from here. The third case I'm going to talk about will be my rim seal with stator vanes but no rotor blades. Again, I remind you of the configuration from the University of Bath with vanes and then no blades. So here, the knowledge built from the previous studies done, verification and validation, was used to build this grid, generate a grid based on the velocities in the flow and the flow parameters given. So it was ensured that the y plus of the first grid point of the walls, as usual, was less than 1. There were at least 5 cells within a y plus of 5. And then the delta r plus, delta z plus, and r delta theta pluses were all less than 20 for this grid build. On the left-hand side, I show the grid when I take out the vane. And then in the middle, or the second set of grids, I show the grid I generated when there are vanes. Here I show the Telly criteria, and here again, the Telly criteria shows that the LES IQ must be greater than 0.8. Both grades were able to meet this criteria. And then I'm using the Kolmogorov scale again to see the time scale that I'll need to resolve the seal. I show the picture with the configuration without vanes as well to see that if you take out the vanes, what are some of the changes, or what you need to resolve the flow. So when there are no vanes for this same configuration, but when you take out the vanes, you need just about 10 to the power minus 5 seconds to resolve the flow in the small scales in the seal. However, when there are vanes, the trailing edge of the vanes and then very close to the seal, you will need at least 10 to the power minus 6 to resolve the small scales there. Then again, I showed the energy spectra from the radial velocity for the two configurations, and then I showed that the grid that I'm using is sufficient for the study because they follow the Kolmogorov -5 test law before falling drastically. So on validation, I'm going to show the effectiveness for the configuration with vanes, with 2 vanes, for RANS and LES as compared to experimental data. The sealing effectiveness beta here depends on this the carbon dioxide concentration in the annulus, and then also on the stator wall, and then also in the sealing flow. So here, the points that I'm showing are the points in the black with the very big black dots are the points that were measured on the experiment. And when you come to the left-hand side with the plots with the circles are from the experimental data from this stator wall. And so I show the LES and then I show the RANS. With LES, it falls directly on the experimental data to show that there's a lot of ingress and the seal is not a perfect seal. But for RANS predicts no ingress, so it predicts a perfect seal. It shows that everything is perfect, but in actual sense, there's ingress. So LES is able to predict ingress, but RANS is not. Surprisingly, even though RANS is not able to predict ingress as compared to LES, RANS predicts comparable CP values for different points in the seal region. So point A is 2.5 millimeters away from the stator vein trailing edge, and point B is on the outer casing in the annulus, in the middle of the seal. So as compared to experimental data, RANS and LES predicts very comparable CP. So CP has been touted in the literature as a predictor of ingress. So we will need to verify this, and we will need to see why, even though RANS and LES are able to predict CP on an equal level, RANS is not able to predict ingress. So now for the results section, I'm going to talk about flow mechanisms and trajectories for rotationally induced ingress for the Akin configuration. So Raps and Orr in their 2009 study stated that in order to have carbon-anomalous instabilities, there must be a lot of swirl in the hot gas flow. However, this study found that even without swirl from the main gas flow, carbon-anomalous instabilities still form. I show a lot of it on the right-hand side, in the far right, a picture that is very close to the rotor disk. But then I'm going to show more plot here. Carbon-anomalous instabilities form from the interaction between the hot gas flow in the axial direction, which I show in the red arrow, VH, and then the boundary layer flow in the azimuthal direction above the rotating rotor, that is omega R0 here. So this pressure is the instantaneous pressure, and then the instantaneous velocity, which shows that there's a lot of carbon-anomalous instabilities that form. Another phenomenon that is seen is vortex shedding, where a vortex is shed very close to the edge of the stator disk, and then it travels along the shear layer, and it impinges on the rotor disk. And then once it impinges, the cycle starts all over again. So here, this is also an instantaneous pressure form plot. And now the alternating regions of high and low pressure about the rotor surface is created by the carbon-anomalous instabilities and the vortex shedding. And these high and low pressure regions are statistically stationary and do not rotate with the rotor wall. So on the left-hand side, on the bottom left, I show the mean pressure plot with LES and then RANS with sealing flow and then without sealing flow. And we could show that the LES shows a lot of dynamics in the seal. On the right-hand side too, I show the time average pressure from LES for when there's sealing flow and when there's no sealing flow. And you see that there's a lot of dynamics in the seal. And also when there's sealing flow, the pressure is higher in the seal. The seal is pressurized. I show another plot where I compare LES to RANS, mean pressure. And you can see that with RANS, there's not so much going on in the seal, hence the perfect sealing showed. There's no ingress observed for the RANS simulations. So the alternating regions of high and low pressures cause the ingress to start on the rotor side of the seal, and then it gets entrained by the shed vortices, and then it goes in through the stator side. Now, it is important to know that not all the sealing flow that goes into the seal is injected into the hull space. Some of it spirals out and then still goes out of the seal. Then on egress, it starts on the rotor side because of the disc pumping action of the seal, and then it gets entrained by the shed vortices, and then it gets out of the stator disc. This is for rotationally induced ingress. And I show 3 trajectories for ingress, where for one trajectory, the flow flows off and then it flows out on top of the seal. And then for another trajectory, the flow recirculates in the seal and then it gets out. And then for another trajectory, it recirculates and then it gets ingested into the hull space. On egress, some of the flow comes out through the disc pumping and then it gets entrained and then it goes out of the seal, or it gets recirculated back into the hull space. Now I'm going to show flow induced by stator veins and their trajectories. This is from the back configurations when there are veins. So for both RANS and LES, the same back pressure was used, but with veins, you can see that RANS shows a much lower pressure than LES, this is because LES shows more pressure drop from the stator veins and also the blockage and then the secondary flows. However, I put in an insert here to show that when you are traversing a vein pitch, the pressure range maximum minus minimum are similar across a vein pitch, hence the similar CP values predicted. So across the vein pitch, the maximum minus minimum pressure is equal, but then RANS generally predicts lower pressure than LES. Yeah. Hence, they are similar CP. Now, I'm showing the mean pressure at 3 RC planes in the seal for the configuration with veins. And I show here over about, I think, 1 vein pitch. And so here, I didn't put the RANs, but I'll flip a bit in between these two plots. So here you have from the hull space of about 6,500 pressure to about 8,000. And for RANs, in the hull space, you have about 2,000 to about 2,500. So you can see that LES predicts a higher pressure drop from the annulus into the hull space, hence the ability to push flow into the seal as compared to RANs, hence the ability to observe ingress. Now with veins, now this is from RANs, and then here I show TKE and 3 RZ planes with RANs and LES. From LES, see that there's a lot of TKE predicted in the annulus region and then in the seal region, and even in the hull space, very close to the seal region. But with RANs, not so much is predicted. Now, the higher TKE predicted by LES affects the pressure losses predicted by LES, and as such, LES predicts higher pressure losses induced by the stator veins. Again, I show another plot where I'm looking at the mean pressure at the plane in the middle of the seal for RANs and LES. So here, you see that 3,005 to 1,005, and as compared to 9,000 to 6,000. So there's a higher pressure drop going from the annulus into the hull space. Hence, LES is able to predict ingress because the higher pressure drop, pressure goes from high to low. So it is able to move from the annulus into the hull space. Here, I show the mean radial velocity in the middle plane in the seal for both RANs and LES. And you can see that the number of highs, the magnitude of the radial pressure, be it a higher magnitude like outward radial pressure or inward radial velocity, are similar for both RANs and LES. However, due to the difference in the pressure drop across the seal from annulus to hull space, LES is able to predict more ingress, or actually predict ingress in the seal region, where RANs is not able to. That is beneath R is equal to R naught, where the hub of the disc is, of the rotor disc is. So now the number of highs and lows correspond to the number of stator veins that you have. So now I'm using two stator vein passages, so I see 2 highs and 2 lows. However, LES is able to predict ingress where RANs is not able to. And then this is just a brief picture with mean radial velocity in another plane, in other planes, to show that there's ingress here going into the seal. And I show the same for RANs, but in the seal, RANs doesn't predict any ingress. Here I show the rate of work per unit area on rotor walls. So on the rotor walls, very close to the seal, that is around Z is equal to 0. There's a lot of work output that corresponds to the number of stator veins. However, away from that, there's no work, the work predicted by the LES is much lower than the work predicted by RANs, but very close to the seal, LES shows a higher work output. Now, the trajectory of flow into the seal depends on the position along the vein pitch. So for ingress, when there are stator veins, how or where the flow goes into depends on where on the vein pitch it originated from. So the flow can either go into the seal and go straight down, or it goes in and then gets swirled onto the left, or goes in and then gets swirled onto the right, depending on where it originated from. For egress, it starts on the rotor side due to the disc pumping action, and then it gets out from the rotor side. Now, I'm going to show for the back configuration, no vein versus vein, to see how if you take veins out, what happens, or how the vein influences the flow. So first of all, I show the first two. On the left, I show no veins, and then for RANs and LES, and then on the right, I show with veins for RANs and LES. And then when there are no veins, you can see that even LES does not predict any ingress. It shows a perfect seal. But when there are veins, LES is able to predict the ingress accurately. This is the mean pressure in the middle of the seal, the plane in the middle of the seal. On the left-hand side for no vein, on the right-hand side for the configuration with veins, but on the top two are for LES, and then the bottom two is for RANs. You see that without veins, the pressure drop across the seal from annulus into the hull space is much lower. Although for the LES one, we do see some Kelvin-Helmholtz instabilities here. And then also the pressure magnitude predicted when there are no veins is much lower than the pressure magnitude predicted when there are veins. which means that the vanes also induce a higher pressure drop. And then also with vanes, the pressure difference in the annulus and the seal region depends on the position along the pitch. But here, without vanes, we see some vortex shedding here in the seal region. Okay, this is from RANS. Without vanes, the pressure drop predicted is much lower. And then for TKE, when there are no vanes, the TKE predicted both for LES and RANS is much lower, which shows that the stator vanes induce high turbulence in the flow. And then again, for mean radial velocity, when there are no vanes, you see that the magnitude of the radial velocity for when there are no vanes is much lower as compared to the configuration with vanes, both for LES and for RANS. So in summary, the following were made for the Rotor-Stator configuration without vanes and without blades, that based on this LES study. It shows that the interaction between the hot gas flow in the axial direction and then the azimuth, and then the boundary layer flow in the azimuthal direction induce a rotating rotor. A rotating rotor causes carbonymous instability to occur. Also, the hot gas flow over the seal induces a series of recirculating flows in the seal, and this causes the vortex shedding at the seal's backward face instead. The carbonymous instability and the vortex shedding creates regions of high and low pressure drop, which are statistically stationary and do not rotate with the rotor. Now, the alternating regions of high and low pressure then cause ingress to start on the rotor side for rotationally induced ingress. And then egress starts on the rotor side and then exits from the stator side because it gets entrained by the shed vortices. Also, LES with wheel model is able to accurately predict ingress, whereas RANS with SSC model could not. And also, when REW over RE phi is much less than 1, rotationally induced ingress is dominant. This is for rotationally induced ingress. And then for ingress induced by stator vanes, both LES based on the wheel model and the steady RANS based on the SSC model can accurately predict the coefficient of pressure on the stator platform. However, LES could accurately predict ingress, but steady RANS cannot. Therefore, CP is not a correct predictor of ingress. Now, LES predicts higher values of TKE in the annulus and the seal region than RANS. So for RANS models to be able to predict ingress, they must be corrected to produce higher levels of turbulence in the seal region. The stator vanes induce higher TKEs on its own in the annulus and the seal regions. Also, the higher TKE values predicted by RANS when they are vanes correspond to the higher pressure drops predicted by LES, And we should also show the mechanism and flow trajectory of ingress and egress induced by stator vanes. So that is my talk for today. Thank you.
Okay, thank you, Sabina. I know we're all online, but I'm going to clap right here. Every time. Okay, so I'm going to open up so Sabina, maybe let's not share your screen for a minute.
Okay.
We can see everybody, but then we can open the screen as needed. So do you have any question from the audience for Sabina, her presentation? Any questions from the audience? Okay, so hearing none, I want to thank Sabina's committee, Professor Greg Blaisdell, Professor June Chen, and Professor Guillermo Paniagua. So I'm going to excuse, sure, no questions from anybody? Okay, then I'm going to excuse the audience and only the committee member can stay. So, and also I'm going to stop recording.
Okay. Thank you.
I'm going to stop recording.